Okay, today we're doing topic 2.8, inverse functions.
All right.
Inverse functions, okay? You've already done this before, but it was last year, so this is kind of a review. An inverse relation will undo a given relation. So two functions that are inverses are the reciprocals of each other, or they're undoing one another.
Like E in natural law?
Yes, like E in natural log. Yes, exactly like that. Every inverse function can be found by switching each x and y value. Every inverse relation can be found by switching each x and y value. Okay? Nikki, this is where I told you we might want to start color coordinating because these get real swappy. Okay? In some situations, this process is intuitive, but other times this may not be as obvious. In these cases, it's important that we understand the concept of inverse relations as they will help us tackle a variety of problems. So what is the concept? What's going on here? It says let's look at this numerically, which is in tables, and graphically, which is in pictures, and analytically, which would be in equations. I prefer the equations because I like to math it. But that's fair. All right, so just in these tables, it says find the inverse relation. Okay, so all we're going to do here is switch x and y. So if on my first relation I have 1 comma negative 1, then on my second relation, that point is now negative 1, 1. Just switch them. So on the first, I have 3 comma 2. So on my second, I'm going to have 2 comma 3. So the outputs and the inputs are reversed. That makes 0 and 4, and 2 and 6. So far, so good. Okay. It says the original table blank a function. Is or isn't? Is. Okay, why? Because each blank has exactly one blank. Because each what can't repeat? An x value can't repeat. So because each x value has exactly one y value. In other words, x can't repeat. Okay, that's what you're trying to say. X cannot repeat. I cannot have more than one input for every output. However, the blank, or the inverse, is what? Not a function. Because, what repeats? Okay, because the x value 2 has 2 corresponding what? Output values or y values. So right here's our trouble. When we see 2 comma 3 and 2 comma 6, that's why it's not a function. Okay. Put it on my desk. No, I'll fix it for you. Did you have any other questions? Okay. Huh? Uh-huh. Mm-hmm. Okay. I think so. Any questions on that so far? Everybody okay with the inverse? Okay. All right, so now we're going to look at some pictures here. You're welcome. Thank you. It says sketch the inverse relation of the given graph. And I really like the steps that you see over there on the side. These right here. Everybody focus right here. 1, it says list the key points in the table. I think that's a great idea. So we are looking at this function. I think it's really nice to go in and say, hey, what are some x and y values from this particular picture? What do you see? Negative 2, negative 1. What else? Negative 1, 2. What else? 2, 1. Last one? 4, 3. Those are some nice points, right? If we're supposed to graph an inverse function, all we have to do is switch those values. So for my inverse function, instead of negative 2, negative 1, I'm going to have negative 1, negative 2. I keep saying inverse function. That's not guaranteed. For the inverse relation, that would be more technically correct. Okay. So create a new table for the inverse by switching the x and y values. And then, what do you think comes next? Plot your new points. Plot your new points. So we've got negative 1 comma negative 2. That gets kind of twisty in my head when I start looking at like just trying to flip these ordered pairs. I like the table idea better. And I like to not look at the old function while I'm trying to plot the new function. Because I don't know, in my brain it kind of gets all messed up. And 1 comma 2. And 3 comma 4. Okay. So now we connect the dots, right? Again with the twisty.
Wait, so do you still follow the same order?
Why wouldn't you go to
Yeah, because I went to 1 and then to 2.
1, 2, then down, then back up? Because it's not how they show.
Are you following the order of the table still?
Follow the order from the table. So we're going to connect our negative 1, negative 2 to our 2, negative 1. And then we're going to connect the 2, negative 1 to the 1 comma 2. And then connect the 1 comma 2 to the 3, 4.
That makes it to where it's not a function anymore.
Oh, it's not a function anymore. So the question says, is the original relation a function? Is the original relation a function, the blue one? Yeah.
Why is it?
Is the inverse relation a function? No. And por qué no? Why is it not?
Because it crosses back up. It doesn't cross the
Where does it fail the vertical line test?
at that part it crosses.
At that part it crosses. It fails the vertical line test in between 1 and 2. So how might we say that?
At the interval.
At the interval from 1 to 2. I like it. Or, so I put as inequality notation. Or we could say on the interval from 1 to 2. You just put no. We know it's not. It would be nice to tell why it's not. Okay? And so that happens here. If I were to try to draw vertical lines between 1 and 2, it definitely crosses this relation
Like 3 times.
3 times, definitely more than once. Right? Any questions on that? Why the new relation is not a function? Okay. Graphical properties of inverses. So this is something kind of neat. I don't know if you saw this or not. If I erase my pretty vertical lines. It says the graphs of inverses are blank over the line blank. The graphs of inverses are reflections over the line. This is not new, but it may have been a long time since you thought about this. What's that line? Y equals x. It's the parent function of a linear equation. Y equals x. He said the parent function. I'll take it. So inverses are reflections over the line y equals x. That is the same every time. That always happens. Okay.
Oh, yeah, if you turn it like diagonal, you can see.
So you can do this with like quadratics and all that.
Mm-hmm.
If that's your favorite function, wouldn't that mean we can also alter it?
Huh? Yeah, but you can't alter it and see inverses. Yeah. It's the parent function of a linear equation. All right, let's keep going. The next page has, how do I do, we've done inverses on tables, numerical inverses. We've done inverses on graphs. And then this is going to be, how do I do inverses on analytical problems or equations? Okay, so there are steps to finding an inverse equation. Do you see the box? The handy dandy box? Okay, steps to finding inverse equations. 1, switch the x and y values. So we're going to swap x and y. And then number 2, solve for y. So switch x and y and then solve for y. Say again?
Would it be better for this to be written y equals blah blah blah, so it's f of x equals blah blah blah?
So for the purposes of actually solving for y, yes. But then step 3 says if original equation was in f of x form, then you're going to write your answer in f inverse of x form. So yeah, he's saying, wouldn't it be easier if these were written as y equals so that we could just switch x and y? Yes, I think so. So I would write example 3 as y equals 3x minus 7. Y equals 3x minus 7. Now, literally replace x and y. So I'm going to write it as x equals 3y minus 7. That's step 1. Swap x and y. And then solve for y. So we're going to add 7 to both sides. 3y equals x plus 7. And then what? Divide by 3. So y is equal to, you could write 1/3 x plus 7/3. You could write it as x plus 7/3, right? In which case I'm dividing x by 3. And I'm dividing 7 by 3. Or if I really wanted to see the slope of this line, I could write it as 1/3 x plus 7/3. You see where I got that? Okay. This would be the new function, y equals 1/3 x plus 7/3. But they want us to make sure that we are writing the new equation, if it is the inverse function, as f inverse of x. So we'll do f inverse of x is equal to 1/3 x plus 7/3. That f to the -1, it looks like f to the -1 power. It's not a power. It's a notation that says this is the inverse function. Okay, so the inverse function of f of x is written as f inverse of x. F inverse of x. Okay. Notice that my first equation had y is equal to 3x minus 7. And instead of subtracting 7, now I'm adding 7. And notice also that it was 3 times x. And now in my new function, everything is divided by 3. Can you tell that it's just backwards?
So you
Okay.
can really just flip.
The operations, which is what we did. Okay. If we graphed both, you would see a reflection over the line y equals x. It would run right through the middle of them. All right. So now we have finding inverse functions of rational functions with multiple x values. So this is going to be a little bit more involved. This is a process that is super handy for moving forward in AP Calc. This is a process that we go through pretty often. And we also did this same exact process today in a physics problem. So understanding how to get from one side to the other, these are big skills that we can really work on this year. Okay, so the first thing, this is a rational function. Okay? We're going to switch the x and y values first. So this says right now f of x equals x minus 2 divided by x plus 3. You want to rewrite it as x equals y minus 2 divided by y plus 3. Now we want to get the y values by themselves. Okay. Right now, I've got y minus 2 over y plus 3. So we're going to have to get everything on the same level. I've got a rational function on the right side. Step 2 up here says multiply or distribute both sides by the denominator of the rational expression to eliminate the fraction. So we want to get rid of the fraction. We're going to multiply both sides by the denominator. So multiplying x by y plus 3. Now we have a monomial x times a binomial y plus 3. Okay? X times y plus 3. Meaning, what do we need to do with that y plus 3? Yeah, we need to distribute the x. Okay? We're not going to be able to just say xy plus 3. It's going to have to be xy plus 3x. That's why they say distribute. Make sure that you catch that. Step 3, we're still trying to isolate y. So we're going to move everything that has y to the left and everything that doesn't have y to the right. You with me? Move everything that has y in it to the left and everything that doesn't have y to the right.
What do you do with the x?
What's the
So I have xy minus y on the left side. And I moved the negative 3x to the other side with the negative 2. Yeah? Okay. What's the benefit of getting everything with y to one side of my equation? I can divide by y. Or I can factor it out. You see that everything on the left side has a y in it now? All of my terms have a y? So what I can do with that is I can pull y from that binomial. So what's left? If I pull y out of xy, what's left? X minus 1, good, is equal to negative 2 minus 3x. So I factored out the y. Now what? How do I get it by itself? Yeah, divide by everything that's over there with it. It's y times x minus 1. So if I divide both sides by that x minus 1, I can get y by itself. Okay. So that last step there is to take y times x minus 1 and divide by that x minus 1 on both sides. So y is equal to negative 2 minus 3x all over x minus 1. So we factored out the y. We divide both sides by whatever's left. We get y by itself. And then the last step, step 6, says rewrite it with proper notation. Now that I've solved for y, this is the inverse function. So f inverse of x is negative 2 minus 3x over x minus 1.
How did you flip the
Why do you
2 and that's
Yeah, Nikki doesn't like it. He would prefer that it was negative 3x minus 2 over x minus 1.
Where'd the other one? So we had x, y minus 1.
We pulled it, factored it out. It went this guy.
Why was that number by square?
We factored it. We divided both terms by y. Factored it out as a GCF. Okay. Questions there? Okay. This is, like I said, this is a long process, but this is something that we do really often. So it's a good process to have figured out.
Oh, you didn't swing the, oh, you swung the negative 3 instead, oh, I swung the 2 instead of the negative 3, that's all messed up.
Oh.
So it's the same thing.
Yeah.
It's the same thing. So you have
Yeah,
negative.
because mine comes out positive. I was just confused, because you have 2 negatives on one side, so it comes out positive, and mine was 2 positive at the beginning. That's what I was confused about that.
Okay. So let's try the next one. This is g of x. Is it okay if I erase what I've got up here? Is everybody in a place where that's okay? No, he says.
Oh, you just flipped it. Okay, yeah.
Yeah. Okay. So I'm going to erase this stuff. Well, I apparently have to erase one little stroke at a time. It's fine. It's fine. It's going to be great. Here I go. Okay, that looks dandy. All right, so we're going to replace X and Y, so switch them. You can do this one on your own if you'd like. Would you like? Did you already? Okay, so I'm going to work it really quickly. Exact same process. Are y'all working back there?
I have no idea what I did.
Try a new one. Oh, good call. Good call. Thank you, Grace, for realizing that there's a G. The function was G of X, so the inverse function is going to be G inverse of X instead of F inverse of X.
Well, you don't, because they might lose one.
All right, it says we know that to find an inverse, we simply switch the X and Y values, okay? Graphically, this means that a function and its inverse will be reflections over the line y equals x. We just saw that. If a graph is not made up of simply line segments, sketching the inverse can be challenging. To do this, we use the fact that a function and its inverse are reflections over the line y equals x. This helps us sketch it. So it says sketch the line y equals x on the graph. If we're supposed to sketch an inverse function, which means we're supposed to flip it, we're supposed to find the inverse, this is hard to do. So the first thing you want to do is sketch the line y equals x. So down here on example 5, go ahead and draw the line y equals x. Any points that are already on the line y equals x are kind of like bonus points. Those are points that are not going to flip. Okay? Now, I would mark a couple of extra points. So any points that are already on the line, you want to label. They're not going to flip. I would mark a couple of extra points. So let's say a good point to mark here would be this one at 0, 4. 0, 4. And maybe this one at 2, 0. Right? So on my inverse function, I'm going to get to use the inverses of those 2 points. So instead of having a point at 2, 0, I'm going to have one at 0, 2. And instead of having a point at 0, 4, my inverse function is going to have a point at 4, 0. Okay. My inverse function is also going to cross through the points that are on the line y equals x. So if you use those points, you can kind of see how your inverse function comes out.
Now, is it always like you start at 0 and it's 1, 1, 2, 2, 3, 3? Is that always y equals x?
Yes.
Okay.
For every x value, you have an equivalent y value. Okay, so you try B. Remember to start by drawing the line y equals x. That'll help. It's pretty hard on this graph because the graph's not to scale.
I found out what I was doing.
Good.
Oh, we're supposed to be drawing.
The good news for you guys is on the homework where this is the problem, they accidentally left the solution filled in.
What are the tables going on?
My point right here is not exact, but it's pretty close. Huh? It's hard. Are we okay? All right, let's go to the back page. We can get this done really quickly. Last page. It says, what do inverse functions do? This is still on the page prior. This is at the bottom. If you plug a number into a function, it generally will output a new number. For example, if we plug x equals 2 into this function, we get what? 5. Right? Now, if we plug that answer 5 into the inverse function, the answer should be what? 2. Good. This is because inverse functions essentially undo the other function. So if we plug x into a function and then plug the output into the inverse function, we should end up with x again. Okay? So two functions, f of x and g of x, are inverses if and only if their compositions give us x each time. If I plug one function into the other and get x, and then I flip it, I should also get x. That's how we know they're inverses. It says to show that two functions are inverses, we must show that the compositions of both equal x. We must show that the compositions of both equal x. So it says, let f of x and g of x be the functions below. Determine if f and g are inverses. So how we do that is we take our f function and we plug in g for x. So I have 2 times half x plus 3 halves. What happens when I push this 2 through here? It becomes x plus 3 minus 3, which is x. Okay, alternatively, I have half times, open parentheses, instead of x, 2x minus 3. So I'm starting my g sentence and I'm plugging in f in place of x in the g sentence. Now I push the half through and I have x minus 3 halves plus 3 halves, which is just x. So we can tell they are inverses. They are inverses. Okay? So if we did that here, show that h of x and k of x below are inverses. Why did they stipulate here that x has to be greater than or equal to 10?
Because that means the graph is inverted.
So on k of x, we don't have some kind of imaginary situation, right? So if we show that they're inverses, that means I'm going to put k of x in place of x into h of x. I'm going to do right now h of k of x. So that means I have the square root of x minus 10 squared plus 10. And what happens when I square a square root? So x minus 10 plus 10 makes x. If I were to plug h of x into k of x, I'm going to have x squared plus 10 minus 10. Those 10s are going to cancel. What's the square root of x squared? X. So h and k must be inverses. Okay. I'm going to let you do example 8 on your own. Okay. You have enough information to do your homework. I'll work it out before I stop recording. If you want to catch the end of it, you can go watch the YouTube video after I get it posted. Okay. Hey, on Friday, we're grading both 2.7 and 2.8 assignments. That ought to give you time to get them both done. Not yet. Keep it. Give me just a second to finish working this one out. Bye. Y'all have a good one.